Perfetto. And then you go full screen.
Okay, thanks a lot. But okay, we are full screen. Okay, so this is, as the title suggests, a talk about the cosmology that we can do with the clustering of galaxy clusters. And I will present some relatively new results that we obtain on constraints on the cosmic glow rate from Redshift-space clustering anisotropies. And I will try to explain all of these words. Okay, this talk is based mainly on this first paper you can see here, which has been published last year with this group of collaborators. And the paper is, so it's about Redshift-space clustering analysis with a new sample of big sample of galaxy clusters. We have also published a second paper on the 3-point correlation function, in particular the baryon acoustic oscillations, the first detection of baryon acoustic oscillation in the 3-point correlation function of galaxy clusters by Michele, but I will focus in this talk on this first paper. And then we have also a third paper in progress on the joint analysis of 2-point and 3-point correlation functions. Okay, so let me okay, so this is a brief overview of this talk. I will first of all explain what are Redshift-space distortions and why we use clusters for this analysis, and I will show you how we can use this as a novel probe to test the gravity theories on the largest cosmological scales. And so this is a sort of test also of space-time structures, because we know that gravity is the structure of space-time. Okay. The goal of the work in particular is to constrain the linear glow rate of cosmic structure that I will define in a while, using the 2-point statistics of galaxy clusters in configuration space. We used a very very big spectroscopic samples of optically selected clusters from the Sloan Digital Sky Survey, which is now public. The spectroscopic, well, the photometric catalog is public. The spectroscopic sample consists of more than 43,000 clusters in this redshift range you can see here, from 0.1 to 0.42. One of the big advantages of using clusters is that we have also the possibility to measure masses, and we did it through scaling relations calibrated with X-ray and with lensing data. The data set at the end is given by transverse and radial wedges of the 2-point correlation function. All of this I'm going to describe what does it mean. The results of the analysis is a first constraint on the linear glow rate from cluster clustering, which is the first ever constraint from cluster clustering alone. And this is the results, which is perfectly or almost perfectly consistent with the general relativity predictions. So let me introduce briefly the topic to go step by step. So first of all, we can define what we call the overdensity field. Is simply this object here. So we have a density field rho at each point in space, of course, can evolve in time. This other symbol here means the mean value of the density field. Okay. And so we can construct this overdensity or density contrast field, which is a continuous field, can be understood as a continuous field of matter. And of course, we can obtain this only from tracers like galaxies, for instance. And in that case, it's just a matter of at each point to define a region around the point and count galaxies and divide by the volume, co-moving volume, or with more sophisticated filters. So when we have the overdensity field, we can define what is this 2-point correlation function, which is simply this, so the average of the density field into different positions. And so this is something proportional to the variance of the density field. If the universe is isotropic, this depends only on the distance module, because for every base it is independent, this function as a function of directions in an isotropic universe. And if we have a set of a discrete set of tracers, like galaxies. For instance, we can express this two-point correlation function, in this case, as the excess probability of finding pairs separated by a given comoving distance with respect to a random distribution. So this is the probability, this is the comoving number density. Okay. Okay, maybe like this. Okay, now the other. Okay, let me see if I can. Okay, 1, 2. Okay, and VV are the comoving volumes. So this is the very simple way of estimating this second order statistics of tracers. And with these equations, we see that there is the close connection between two-point correlation function and power spectrum, which is particularly convenient in cosmology because we can predict what is the matter power spectrum as a function of the cosmological model. And so then we can relate to these things that we can measure. However, even if the universe is isotropic, the way in which we measure distances in the universe introduce anisotropies. The reason is that this first equation, which is valid in a homogeneous universe, so it expresses the relation between comoving distances as a function of comoving redshift and the Hubble function, so the logarithmic derivative of the scale factor, is true for an homogeneous, so large-scale universe. However, what we measure is not this redshift, but it's something that at least contain another terms, which is related to the peculiar velocity, the peculiar velocities of objects along the line of sight, plus other relativistic corrections that can be neglected at first order, plus redshift uncertainties. But anyway, the first term that we can see here introduce an anisotropy if we substitute this Z observed redshift into these equations. So since this object here is something that we cannot directly measure, in several cases, in the first equation we use the sum of these two terms instead of simply Z, and so we introduce an error. This error depends on the line of sight, and so introduce an anisotropy. And the good point, however, is that it is related to the peculiar velocity, and so from these distortions that we will obtain in the map with this error, we can constrain the peculiar velocity field. So basically the effect of space-time distortions, but at small scales. While the first one is the effect of space-time distortion at large scale. Okay, so in order to use these things, we, as we have seen, we measure the two-point correlation function. And the point is that, I skip a lot of equations, but the point is that we are able to predict the distortions in the two-point correlation function, the anisotropic two-point correlation function, and this model depends on some bias parameter and other parameters, but in particular on the linear growth rate, which is defined here. So the linear growth rate f, which is the logarithmic derivative of the linear growth factor, something that directly depends on gravity, and in particular in general relativity, we can approximate this linear growth rate in this expression. In alternative gravity theories, we could have that 0.55 is not that number, but another one, or even a more complex function of this. So the message is that if we measure the two-point correlation function and we, in some way, we can constrain the distortion, the redshift-space distortions introduced by the fact that we use the observed redshift in the equation to derive comoving coordinates. We can model this, and from the modeling, we can derive constraints on F. That basically means constraints on the gravity theory at the larger scale. Okay, so why clustering and not galaxy clustering? So the main probe is galaxy clustering, but and the reason is that you need a huge sample of objects to reduce noise, shock noise. And this is a big advantage, of course, for clustering. However, there are also advantages. The first one is that galaxy clusters are highly biased tracers. That in cosmology simply means that the signal is higher. So the normalization of the two-point correlation function is higher with respect to galaxies. So higher noise, but also higher signal. Cluster clustering is relatively less unaffected by the same distortion, but at small scales, which are non-linear distortions called fingers of God, that are not directly related to cosmologies and are also difficult to model directly. And so the fact that cluster clustering is less affected implies that possible systematic uncertainties in the model are lower. At the baryon acoustic oscillation scale, we have a low damping. So and this will be exploited in the third paper in particular, because in this work here I focused at smaller scale with respect to BAO. And finally, we have some possible different ways to estimate cluster masses. And this is very interesting with respect to galaxy clustering, because we can use this information to put constraint, to put a prior on the bias, on the effective bias of the sample. Anyway, to really do clustering analysis in a competitive way with respect to galaxies, we need an extremely large sample of clusters. And so in the past, this was not really possible or competitive, but now we have these big samples. And so it's something that we can try to do. And in fact, it's what we try to do. So we use this photometric cluster sample. So cluster selected by these three authors, you can see here in 2012, very big sample of galaxy cluster. This is the number in about 15,000 square degrees of the sky and in this redshift range. The same authors in 2010 estimated the scaling relation using different set of data. And so we have this relation between richness, which is something that we can measure, these things, and the masses. And from this catalog, we sub-selected a spectroscopic cluster sample, which is particularly important for this kind of redshift-space distortion analysis, because we want to have very small redshift errors. And we did it cross-matching with another public catalog, which is the Bose spectroscopic galaxy sample. So all the data are public in this case, and we arrived at a sample of this number, 43,743, in a reduced square sky area of this, and this is the mean redshift. Okay, so this is a picture showing the map of this cluster catalog in galactic coordinate system. Different colors are just, so the gray is the original photometric sample, and all the other colors are show the spectroscopic catalog we obtained. So as you know, clusters are the biggest structures in the universe, but in this case are just points, are mass tracers. So each point is a galaxy cluster. And these are redshift mass distribution of our sample in the different cases. So the green was the original photometric sample, and then the black is the cluster in the Bose area. Red ones are the spectroscopic sample selected by the in the original paper. At the end, this blue and gray is the samples we used, and in particular, we selected only objects at low redshift lower than 0.45. So this part is the sample we used because we wanted to have a complete sample or a pure sample without having to rely on the selection function too much. On the right, you can see the mass function, so the number counts as a function of mass, something that, of course, with cluster can be directly used to do cosmology, but if you know the selection function very accurately. So in this case, we didn't use at all this, and we focus on the variance of the field in the part of selecting the sample in order to be almost 100% pure and complete. Pure in the sense that there have been studied by the original authors actually, considering so in some way, let's say, the completeness of the catalog in terms of how many clusters are expected to be found there in several different way of estimating this. And maybe this is the original photometric. Now, the spectroscopic, of course, is not. I mean, it's just a subsample of that particular case. That, of course, is not complete in the sense that several clusters. For our case, then spectroscopic means that we have a BCG with spectroscopic range. This basically means it is in case complete with respect to only the clusters that are BCG with spectroscopic range. In fact, we already discussed the completeness. So if this was the original catalog, we are here, and so we discarded all of these objects in this case. But in any case, the completeness is not really entering any, because we are looking at the variance in this case. Only when we put a prior on the bias, we have to consider only the objects we have, because if we simply convolve with the mass function and do not consider there the completeness, we will have a bias on the bias. But so we estimate it directly with the objects we have. So at the end, and we didn't use the number counts, and so the selection function actually enter only in terms of a geometric selection function to construct the random, but not the part related to the completeness. Then in practice, we have to measure the two-point correlation function, and so we need an estimator. We use the Lenditzel estimator. All of these symbols are just meaning that we count the number of pairs. CC means cluster pairs. S means the modulo of the comoving separation in Redshift-space. It's called S instead of R. Mu is the cosine of the angle between the two objects. Of the angle. The other are just the total number of pairs that we need to normalize. And we need to normalize because generally the random catalogs is constructed to be much larger than the cluster, in this case, cluster catalog. In this case, we use the 50 times larger. And so we need these terms here to normalize. These other terms here, where CR means just the cross pairs between real clusters and random cluster, is just where an estimator which is with the minimum possible scatter and bias. And this is the Lenditzel estimator, something that can be easily obtained from a catalog if you are able to construct a random catalog properly. But in this case, it's easy because we have already the mass of the boss samples and all the weights of boss samples. Then it is particularly convenient. And so in this case, we have a 2D, two-dimensional function because of the anisotropies I mentioned before. In real space, the dependence on mu would be 0, but in a Redshift-space, no. But it is convenient then to go into some convenient basis. Two of them are multiples and wedges. In these studies, we use wedges. That basically means to do this integral as a function of mu. And so we have this clustering. These are called wedges. Okay, so this is the results. So on this, first of all, these are the two-point correlation function in 2D. So the first one obtained with the Lenditzel estimator I showed before. In this case, is the same plot in two different representations. Here we are in Cartesian coordinates, so we have perpendicular and parallel coordinate along the line of sight. In a real space, these are contour lines, so each line has the same value of the two-point correlation function. We would expect circles if we were in a real space. The fact that we do not have circle means that we have distortions. The main ones are the Redshift-space distortion I mentioned before. The same in polar coordinates. In this case, we expect in real space vertical lines. The fact that we do not have vertical lines means that we have distortions. Okay, then from this we integrate. The idea is to have more compressed, let's say, summary statistics that allows us to have an easier way to model these things. And so we did it, and this is the clustering wedges. What we can see here on the left, the points are the two perpendicular and parallel wedges from the equations before. The fact that are clearly separated is the effect of Redshift-space distortion. So in real space, we expect this two set of data coincides. The fact that they are clearly separated is exactly what we want to use to constrain gravity on the larger scale. As always, the error bars here is just from the covariance matrix, the diagonal, the square root of the diagonal of the covariance matrix that we estimated in particular in this case with Bootstrap after several tests. The other symbols you can see here is the lambda CDM predictions, so general relativity predictions that we can see are quite in agreement with the data also from this plot. The gray band is the output of MCMC analysis. It's the best fit analysis we have done up to this minimum scale here, which is 10 megaparsec overage, which is also quite small with respect to what we can do with also galaxy clustering, but in this case was the data were good enough to, and also the model to reach this low separation. Okay, so we ran MCMC, so Bayesian analysis of this. We put strong constraints on Planck cosmology for what is the evolution of the background, so large scale dynamics. Many equations that of course I skip in this talk, you can find in the paper, but at the end we have three combinations of parameters that we can constrain. In particular, f times sigma 8. F is what I defined before, so it's what is related to gravity. Sigma 8 is the normalization of the power spectrum, let's say. The other two parameter is a linear term in the bias model that relates the density contrast of clusters to the density contrast of matter, and B2 is another 3 parameter in the bias model. As I said before, the good point is that we can leave this free with the flat priors, but in clusters we can also try to put a prior from masses that we estimated. This is something that we can do thanks to the fact that we have clusters. So this is what we did, and basically so this as always are the marginalized posterior. In this case, it's very similar to the prior, meaning that we are not really constraining B1 if we set a strong prior, but we can constrain in particular F sigma 8. F sigma 8 that I show here, so this is the marginalized constraint I obtained from in this work, and this is the point. All the others are from galaxies, so galaxy clustering and cosmic void analysis, but not from cluster clustering. This is the first one. General relativity prediction is this black line, so with this 0.55 exponent, parameter we have seen before. This other gray band area, we obtained this analyzing a big set of F sigma 8 and Hubble function data with Michele Moreschi in 2017, and in that case the best fit gamma parameter in agreement with general relativity, but was at 0.65, and we see that this point is in very good agreement with this. That means that it is in very good agreement with the other data we have. Okay, finishing, of course, the point is that we have to reduce this error bars to conclude something. And this is exactly what we are doing now, and we will do with Euclid in particular. So the idea is to try to reduce a lot. The forecast we have, for instance, for Euclid are very promising, of course. The idea to do that, this is not a really test on different gravity theories, but just to show what is the effect of different gravity theories in this case. This is just a few examples. F of R is a model in which in the Einstein hypertensor you have a function of the Ricci scalar instead of just R. This is one particular model of the F of R family. CDE means coupled dark energy. Here you do not have a lambda constant, but you have a field that is coupled with cold dark matter. DGP is an even more strange model in higher dimensions. It's a brainwave model. Of course, we need to reduce these error parts, but we are going in this direction, okay, to really discriminate among different gravity theories. Maybe I finished. So this is the conclusion. Basically, is what I've already said. The final result is that we obtain this. Okay, so as you can see here, this value, which is the first constraints with clustering alone, and that's it. Thank you. Guarda che vi ho scritto. Allora, se ce la faccio, ok, you mean più avanti. Piano piano. Okay, you want to know because the radial wedges seems to be known, but if you estimate the chi-square is paired because there is a big covariance between this point. So this is the error bar are not independent at all. But because if you have more pairs in one bin, you have also more pairs in one bin, and so if you estimate the chi-square, let's say at least simple statistics with the full covariance matrix, it is not a statistical issue. And then if it is real, I don't know, but in general, if you have one point, then also the other points below in the same. But we see similar also in galaxy clustering. Actually, we have to say now that in this particular case, as I mentioned, what I call clustering is galaxy clustering of the BCQ. So it's just a subsample because the center are exactly BCQ. So basically, it's a way of sub-select the galaxies for which we can somehow estimate the masses around of the cluster. And so in fact, we obtain something similar to galaxy clustering analysis that, of course, we use to compare.
Just a question on the comment. So I see that in your results, you have just one point.
Yes, because we could also separate, I mean, differentiating Redshift and so on, but the data are not really enough. I mean, I have other plots from 2 points, but at the end it's not being too much. So this is the average clustering in this Redshift range. So that there is also, let's say, an uncertainty on the, of course, on the data. And so if you have a likelihood, you have to consider that.
Is like, you didn't talk to us about the selection function of this because I mean, when you do cosmology with the mass function, the selection function
is true. Yes. In this case, no, at the level. So to just measure the 2-point correlation function is not important. Actually, doesn't enter the analysis except. Except in the random, let's say in the mean value of the random, but no, I don't know why I wanted to enter maybe here. So just in the mean value prop that anyway then is cancelled. And so the selection function in terms of how many objects we have with respect to what is expected is not does not enter like for galaxy clustering. For cluster, because we are the variance of the density, it would enter if you want to use this sample to estimate the effective bias. In this case, you have the bias as a function of mass and redshift. If you convolve over the mass function, then if there is a selection function there, you have to put in the convolution. In this case, we instead define measure the effective bias directly with the objects we have, averaging. So using Tinker Tal model in this case, and then averaging over all the objects we have, and not others. So in this case, also in that case, this does not enter. Anyway, I tried also. I did not use as to constrain anything, but I tried to put the Tinker Tal prediction on the mass function that we have seen before, and at the low redshift in which we are, also that prediction was quite in agreement. not say I decided not to use it, but it's not necessary. I mean, it's quite consistent at small at low redshifts. What is expected, but anyway, in the clustering it doesn't enter. That is also the reason why we use galaxy clustering in this case without having to consider it. With Euclid, maybe after this story I can show there is a paper. Actually, even the first paper. Okay, we also you can find out in the Maurice paper the expected uncertainties in Euclid, which are extremely. I mean, are basically inside the gray band and at several different redshifts from the main analysis of the spectroscopic samples. Then in Euclid we will also add several other things like cluster, cosmic voids, and so on. You can find so there are in the red book of Euclid actually there is a plot similar to this with several error bars from at least the main probes of Euclid. So we can expect even something better. Which is also not well, it's between the primary goals of Euclid. So even so to have the possibility to discriminate among different tiers. So we expect a huge improvement. Let's say you can expect something similar to the gray band, more or less at the redshift. Well, at the redshift of Euclid, which is anyway quite. So not exactly this part from the main probe list of galaxy clustering.
Maybe you say it already, but you understand better. So your statistics are going to go with Euclid, so you can do better clustering technology, but at the same time you will deliver even more galaxies.
No, in fact, the main statistic will be galaxy clustering. We are working for galaxy clustering and so on. So to reduce the error bars on all the other points.
Will the clustering still remain?
Clustering can add something in Euclid. So cluster clustering will first of all add something to cluster number counts. Let's say, and cluster number counts plus clustering is going to be used as an additional cosmological probes. That means now the requirements of Euclid are for galaxy clustering and cosmic shear, but we have also this plus and cosmic void statistics clustering also cosmic voids. So we hope with Euclid to do this some kind of similar analysis, even with cluster clustering alone. Also, and in that case, clusters are selected from the photometric sample of Euclid, while galaxy clustering that we will use for this are from the spectroscopic sample. So they are also not exactly the same, for different selections. But at the end, the final goal is to combine all of these things. And so in 6 or 7 years from now, we expect to really say something conclusive, let's say, on that.
Questions from home? Okay, now we can say
Questo di là.
perché non trovo il tasto destro è rotto. Io ho dovuto riprogrammare per usare questo. Okay.
Qual è stato?